welcome to this explainer. Today we are unpacking an absolutely epic story of technological evolution. We're going to see how a company founded literally just to make PC games look cooler somehow accidentally built the entire backbone of global artificial intelligence. It's this wild story of how pushing pixels for video games unexpectedly unlocked the massive mathematical horsepower required to simulate human intelligence. And to really wrap our heads around the sheer scale of the shift, just consider the staggering drop in energy consumption. If you're training a massive 1.8 trillion parameter AI model, the exact kind powering modern generative AI, the required power plunges from 15 megawatts all the way down to just 4 megawatts, simply by switching to NVIDIA's newest Blackwell GPU architecture. That is a leap in efficiency that is quite literally reshaping the tech world.
Okay, let's dive into our roadmap for today. We'll be looking at from origins to video games, the limits of CPUs, the solution, graphics processors, the CUDA revolution, the engine of AI, and finally, efficiency and supercomputers. Let's get right to it.
Starting off with Section 1, from origins to video games, and the birth of a graphics giant.
Picture this. It's 1993, and the founders of NVIDIA had a highly specific vision. They truly believed the PC was going to become the ultimate consumer device for video games. Fast forward to 1999, and they launched the GeForce 256. This was a massive, game-changing milestone. Marketed as the world's very first true GPU, it integrated transform and lighting directly onto the chip itself, totally revolutionizing 3D graphics. And the crazy part? Without even realizing it, they were laying the exact hardware groundwork required for modern supercomputing. Moving to Section 2, the limits of CPUs. Really, why central processors hit a wall. So as technology rapidly evolved toward deep learning, the traditional computing architecture started facing a massive bottleneck, which begs the question, why aren't central processing units, or CPUs, enough for artificial intelligence? After all, aren't they supposed to be the brains of our computers? Well, think of it through this analogy. A CPU is kind of like a tiny group of absolutely brilliant professors. They are highly versatile, and they can solve extremely complex equations, but they have to solve them one at a time, sequentially. A GPU, on the other hand, that's like an army of thousands of students. Sure, they might not be able to solve complex logic puzzles individually, but if you hand them thousands of simpler math problems, they can solve every single one of them simultaneously. And when you translate that abstract concept into physical hardware, the structural difference is basically night and day. A traditional CPU relies on just a few incredibly powerful processing cores. But a GPU architecture, specifically what we call streaming multiprocessors, reveals a highly parallel structure packed with thousands of smaller execution cores. That single structural difference changes absolutely everything.
Which brings us to Section 3, the solution, graphics processors. Enter the GPU.
So the graphics card, which originally was designed solely to calculate the math required to render 3D video game pixels really fast, turned out to be the perfect, totally unexpected solution. This birthed the whole concept of GPGPU, or General Purpose Computing on GPUs. Researchers suddenly realized, hey, if you treat data as a massive stream of values, kind of like pixels on a screen, you can use this parallel structure to manipulate massive scientific datasets incredibly efficiently. On to Section 4, the CUDA revolution, and the major turning point in 2006. Now, hardware alone just wasn't going to cut it to change the world. In 2006, NVIDIA totally transcended being merely a hardware company when they introduced CUDA. CUDA was the magic weapon here. Before it existed, you practically had to trick your hardware into thinking general math was actually a graphical image. But CUDA provided a dedicated software library that allowed developers to easily write high-performance parallel processing applications, effectively unlocking accelerated computing for the masses. Let's look at Section 5, the engine of AI, powering the AI boom. This whole invention of accelerated computing is the direct precursor to the massive foundation models we use every single day now, like ChatGPT. Deep learning inherently relies on a pyramid structure of learning layers, which requires the simultaneous calculation of millions of variables. And because GPUs have thousands of cores, they handle all these parallel streams flawlessly, accelerating models up to 3 times faster than a top-tier CPU ever could. And the relentless pace of this innovation becomes so clear when we trace the timeline. From the Tesla architecture back in 2007 to the brand new Blackwell architecture in 2024, overall computational power has increased by a factor of 1,000 in just the last 8 years. Let that sink in. The resulting market reality of this shift is just mind-blowing. When breaking down the 2023 revenue share, the data center slice is absolutely dominant. The company that literally started out trying to make your PC games look better is now overwhelmingly the provider of critical infrastructure for the world's most powerful supercomputers. Finally, Section 6, Efficiency and Supercomputers, scaling up while saving power. Now, as AI models grow exponentially, the monumental energy consumption of data centers has become a severe bottleneck. Extreme efficiency isn't just nice to have, it's mandatory. And this is exactly why the 2024 Blackwell architecture is so vital. We're talking 40 petaflops of AI performance and a 30 times higher throughput. Plus, by using technologies like the NVLink switch, multiple chips can communicate so incredibly fast that they effectively act as one giant unified GPU. But the really crucial takeaway here is 30 trillion watt-hours. That is the estimated amount of energy the world could save annually, which, by the way, is equivalent to the electricity needs of nearly 4 million homes. If all high-performance computing and AI workloads switched fully from legacy CPU infrastructure over to GPU-accelerated operations. This perfectly echoes a statement from NVIDIA's chief scientist Bill Daly, who said, "We can more than triple performance while maintaining the same total consumption." The transition from serial computing to parallel computing isn't just about raw speed anymore. It's literally the only sustainable path forward for the future of microprocessors.
Which leaves us with a truly fascinating question to ponder. As GPUs continue to absolutely conquer the data center, and these AI models grow to trillions of parameters, what is the ultimate future limit of AI scaling and energy consumption? What will the next evolutionary leap in computing even look like to sustain this incredible revolution? It's a question the entire tech world is racing to answer right now. Thanks so much for joining me for this explainer. I hope this helped you visualize exactly how we got here.